class from the Institute of Advanced Studies. She's going to talk to us about
configuration and
configurations. Also, maybe I should make a plug for the AlgebCon conference, which will be this weekend. And we have a nice series of talks lined up, and in fact, Orit will give another talk in that conference on a different topic.
Right. Okay, thank you very much for having me. I'm to be here. So, as I said, the title is unconfiguration combinatorial, and what my goal for this talk is really to point out some connection between the classical notion of rigidity of graphs embedded in the plane and configurations of lines in R3. Okay, so this is the goal. So I will start with defining some notions in combinatorial rigidity. So what do I mean by rigidity of graphs? So we start with some abstract graph. Let's say a triangle. And we can take this graph, embed its vertices to the plane. So now we have 3 points in the plane, and we can look at these distances, or this length, the length of the edges. And now I want to say whether this realization is rigid or not. So what does it mean if it's rigid? So I look at the neighborhood of the vertices, and the question is, can I move the vertices a little bit so that the length of the edges are kept? Right? So this is the question. So of course I can always have some trivial changes, like I can just translate the triangle or rotate it, and then I'll get the same edge length. But the question is, are there other motions? Can I do something else which does not, it's not a translation or rotation, but still preserve these distances? Okay, so of course for triangle, cannot, it's rigid. And here's another example. So if I have a cycle of length 4, so I can just move it a little bit, stay with the same, keep the length of the edges, but not get the same configuration of points. So the two configurations, the first one and the new one, are not congruent. Okay, so this is not rigid. So notice that they started with an embedding of the vertices in the plane, but I almost didn't use the properties of the specific embedding. I didn't have to tell you what are the exact distances. It was something which looks like more property of the graph, of the abstract graph, not the specific embedding. So let me define what I mean. So I have a graph. And I always use n for the number of vertices and m for the number of edges. And I consider this map. So what would it be? So given a graph G, I look at a sequence of n points in the plane. I think of it as an embedding of the vertices of the graph. And I return some vector in Rm. And what it does is it takes n points. And then what it returns is the distances, the I minus ej. Let's say squared, because I want it to be algebraic, for every ij, which is an edge in the graph. So the vertices, I'm not saying it's explicitly, but the vertices are the numbers 1 and 2.
Is the graph planar?
Sorry?
Is the graph planar?
So it is embedded to the plane, in the plane, but it's not planar in terms of the. No. So edges can just.
So isn't there also a notion of some infinitesimal rigidity, but you want the motion to be
yes, but for generic embeddings, so now I didn't even define the notion, but for generic embeddings this will be the same. If it is infinitesimal rigid, then it is rigid in distance. So I say that G is rigid. So definition, G is still rigid. So if the rank of the Jacobian of Fg, the maximal rank, is 2n minus 3. So why 2n? Because we can choose the points. Yes, we have 2n points. But sorry, why this -3? Because we can always have these trivial rigid motions that we can do. But other than that, we want it to be maxima. So we wanted the only motion that we will be able to do is those rigid motions. Okay, so this is the definition. And so there is a characterization of Laman from 1970 that says that G is minimally rigid if and only if so the number of edges is exactly twice the number of vertices -3, and for every subset V prime, so for every V prime in V, the number of edges of the graph restricted to this subset is at most 2. And the intuition is that we can look at this matrix, the Jacobian, and we want the rank to be maximal, so we can always find a subset of the rows. So, okay, maybe I shouldn't get it.
So I don't understand this. So this graph is combinatorial graph, right?
Right, it is.
And so the embedding, so it's maximum over all?
Over all different embeddings. So you can look at this as variables, and just ask about the rank. And okay.
So the matrix is what line? What sign line?
So it will be the number of rows will be as the number of edges.
Oh,
and the number, it will be n times the
And the E prime is strict inequality?
So not strict inequality. If you have more edges, then it means that there is some dependency there, and then here is no. Okay, so this is a result of Laman from 1970, and there's another result, an earlier one.
And also you didn't define what is minimally rigid.
So it means that you cannot remove any edge and still stay rigid. So Enberg showed that G is minimally rigid. If and only if G can be constructed, G can be obtained. From K2, so one can start with one edge, and then construct G by 2 operations, so by 0 extension and 1 extension. So some sequence of either 0 extensions or 1 extension. So what does it mean? So 0 extension is if we have a graph, and then we add a vertex of degree 2. So a vertex, 2 edges. So see 0 extension, and 1 extension means that, so we have our graph again, and we have here, let's say we have an edge, vertices U and V, and another vertex W. So what 1 extension means is we add another vertex Z, which is now connected to U and to the vertex V, but instead of we remove the edge UV, and we add another edge here. This is 1 extension. So what he showed is that if G is minimally rigid, we can always construct it in this way. So these things are equivalent. It's actually characteristics.
But if you just add to one vertex with this, it's not rigid anymore.
No, so you start with a rigid graph,
Yeah.
and then so you didn't have this. You had only this.
Yeah. So start with the segment.
No. So okay, you start with a second. You apply some of the.
W is also a vertex
Yeah,
of
yes.
rigid.
Here you have to have at least 3 vertices.
Okay.
Okay. Okay, so notice that this notion is really a local notion. So for example, there is this graph, which is rigid. So if we look locally, and I tell you the distances, then you cannot move it other than using rigid motions. You cannot really change the location of the vertices locally and keep the edge length. But I can just look at this. They should have drawn something more extreme. They can just flip it there, and then I get the same distances, even though the same length, even though there does not exist a rigid motion takes this graph to this. Okay, so it is still a rigid graph, even though we have this, okay? Because this is a local notion. And so there is a stronger notion of global rigidity. So G is called global rigidity. If for every pair P, so this is a sequence, so this is a vector sequence of endpoints. So every P and P prime and a generic embeddings or realization So if we have two embeddings of the vertices of G that induce these two generic embeddings that induce the same length of the edges, then in order to say that G is globally rigid, the condition is that then they have to be congruent. Okay? And there is also characterization of this. So, in 1988, so he showed that if G is globally rigid, then it must be three vertices connected, and redundantly rigid. So what redundantly rigid means that if we remove any edge from the graph, it is still rigid. Okay? This is one condition. Three connected means that we cannot disconnect the graph by removing two vertices. Okay? Here we can connect one. Here, for example, we can disconnect the graph. If we have two vertices that disconnect the graph, we can always take a projection. Okay, so we showed that these are necessary. Actually, it's necessary also for higher dimensional versions of this, and he conjectured that this should be an if and only if condition. And afterwards, I'm not sure who, but people found a counterexample for dimension greater than 2, and the question stayed open until 2005 for dimension 2. So he conjectured that this should be an if and only if condition. Okay, so then, Connelly.
So when you say higher dimensional version, what increases?
So you're asking because you're standing. Okay, sorry.
Yes. So when you say higher dimensional version, are they still graphs?
You embed the vertices to RD.
I see.
You fix the distance as well. So in 1990, he showed that so one extension. If we take a globally rigid graph and apply one extension to it, or edge addition, if we add n, this preserves global rigidity. And then in 2005, Jackson and Jordan proved that so they completed the proof, so they said that every tree-connected redundantly rigid graph can be obtained from K4, the complete graph with 4 vertices by one extension and edge addition. So we can start with a K4, it is globally rigid, then we just apply these operations and we get again a globally rigid graph. But if every graph with these properties can be obtained this way, and every globally rigid graph has to have these properties, then this is a characterization. Okay, so now I'm gonna move to line configuration soon, but so I want to show a new approach, and the new approach, what it will do, it will replace so one of the things that I will show that some of the results here can be proved more easily. So for example, we will be able to reprove Connolly's result in a way that I found simpler. And also we can show here that for rigidity, 0 extensions and 1 extension preserve rigidity of graph. So this is one thing to do. Okay, so before I'm getting to that, maybe I'll say a small observation. So far,
what is K or K4?
So K4 is a complete graph forward.
Okay.
So you start with that. This is globally rigid, and then you can construct any other. Okay. So observation that I'm not going to state really formally, but it's going to help me in what follows. So observation. So if we look at the set prime pairs of configurations, now I want to look at pairs of configurations because it will be relevant to what's going to come. So we look at pairs of configurations of points. So there are again a sequence of n points in the plane and another sequence, and we require that the edge lengths that they induce will be the same. Okay, so if we know that this set, so I don't want to say it in a precise manner. So if we know that this set has dimension, so has dimension at most, or actually equal to n plus 3, then G is rigid. Okay. And what's behind it? So first of all, if we fix, so we can just take P to be an arbitrary or generic sequence of n points in the plane. So we already have 2 n degrees of freedom. And I want to find P prime, which has this property, which has the same edge length. Okay, so the intuition says that if G is rigid, then P prime will be determined by the distances here, so by P, up to 3 degrees of freedom. So this is the 2n plus. But I'm saying, but it works only, at least in a straightforward way, it works only in one direction, because, so I hope I did it. Yeah, so it works in this direction, because if G is not rigid, then we can find a subset here, which is of dimension larger than 2n plus 3.
I don't know. So these points are you're taking from 2n, right?
So it's, oh, I'm sorry. So it should be,
okay. 4.
yes. Okay. So it's going to show up in what follows, but this is more or less the intuition, and we're going to consider this.
So this is true, or is it?
So actually, it's an if and only if, but at least over C. So I don't want, because the title of the seminar is real algebraic geometry, I try to avoid anything related to But yes, if you look at if you restrict to something which is a manifold, then if you find, so if it's not rigid, you will find a subset which has a manifold as dimension larger than this, and if you can't, so I'll say something more precisely than that. Okay, so now how all of this is connected to line configuration. So the first step is using the Elke-Sharir, is referred to as Elke-Sharir framework. It is actually an idea of Elke as a program on how to solve a very famous conjecture of Erdős, and later Micha-Sharir also developed the idea, they wrote a paper together, set the program to the solution of the problem, which later was solved by Guth and Katz, was almost completely solved by Guth and Katz. So one of the ideas that appeared in the paper was the following. So I don't know if you, okay, so the problem of Erdős asked about, you have endpoints in the plane and you look at distances between pairs of points, and you want to say how you want to have the fewest distances, fewest distinct distances as possible. So the idea of Elke was the first step of the idea was, instead of bounding, somehow giving a lower bound to the number of distinct distances, just look at pairs. So look at or quadruples. So if you
it might be you state these distinct distances problem more formally, because people don't know.
But it's not really relevant. It's just this reduction. If you want to get it, but it's, yeah, I didn't plan to say this is So okay. So I'll say what's relevant to me, and then if you still need to set everything, let's see. Okay. So never mind the context, but one of the ideas of Elke was the following: if you look at pairs of points, so quadruple of points in the plane, so you have 2 points P, Q, and another pair of points P prime and Q prime. Okay, so something very simple. So if the distance between P and Q is the same as the distance between P prime and Q prime, then the very simple property that holds is that there is a rigid motion that takes P to P prime and Q to Q prime, the same rigid motion. To use a rigid motion, just take this interval, send it to this. Okay, so this is a very simple idea. And then another observation that he had is the following: we can look at so we identified R3 with rigid motions. So orientation preserving. Rigid motion. Okay. And so how does this identification go? So it's without pure translations. So orientation preserving rigid motions, except for pure translations, can be described as you pick a point in the plane, and then you rotate with respect to this point with some angle. Okay, so every such rotation can be described as the center of rotation, so it's point AB, and the angle of the rotation. So if you choose this parameterization, it will be cotangent over 2. This point in R3 will describe this rotation. And then, how do we describe such a pair or pair of pairs? So, Elke's idea was to associate with every pair of points P and P prime associated. So, P and P prime. you looked at all the rigid motions that take P to P prime. Okay. So when you look at this parameterization, what you get is that if we look, so this is a subset of points in R3, but because this is specific parameterization, this is a specific subset, what you get here is a line. Okay. So this is okay, so with every pair of points, P and P prime, pair of these 3 points, we can associate a line in R3, and this line will correspond to all the transformation or the rigid, or all the orientation preserved in rigid motion, take P to P prime. Okay? And then what are the properties that we get? So properties. So the first very basic property here is that if the distance between P and Q is the same as the distance between P prime and Q prime, then what it means is that LP P prime, so do you see what? And LQ P prime must intersect. There is a rigid motion that takes P to P prime, Q to Q prime, so the lines so there is a rigid motion on the first panel, LP P prime, and on the second, LQ Q prime, and therefore they intersect each other. Okay, so this is a very simple observation. So we can say this for a sequence of points, because this is what we're going to need, so let's state it. So if we have we have 2 sequences, P1, Pn, and Q1, Qn. And, oh, okay, sorry, maybe I use Pn prime. So they are, so if the lines, so LP, P1 prime, and Pn prime. If they are concurrent, it means that they are congruent with orientation preserving rigid motion. And it turns out that also if they are coplanar, so if they are, so I don't want to write it again, but then, so if they are coplanar, so it's easy to check that what it means is that they are again congruent, but with orientation reversing rigid motion. Okay, so. Okay, I hope it's okay. So, and actually if they are both, so maybe I will try it, but if they are both concurrent and coplanar, what it means is that the first configuration lies on a line, and the second is also on another line, possibly, and they are concurrent. Okay, so I want to somehow exploit these properties and to connect it to the notion of rigidity. So it looks connected. So let's see. So suppose I want to know whether a triangle is rigid or not. This is the simplest example. Okay. So suppose I want to know whether a triangle is connected. So I start with an abstract triangle, but then I can look at 2 embeddings of this triangle to the plane. So I have one embedding with P1, P2, P3, and another one P1 prime, P2 prime, P3 prime. And the fact that they are realizations, so suppose that the distances are the same. So triangle can induce the same distances. Then what does it mean? It means that the distance between P1 and P2 is the same as the distance between P1 prime and P2 prime. So if I look at the lines LP1, P1 prime, and LP2, P2 prime, so this is one line and this is another, but the fact that the distance here is the same as the distance here means that this line must intersect. Okay? And similarly, P2 and P3, the distance here is the same as P2 prime and P3 prime, so the line LP3, okay, so you see where it's going, right? So whenever I have an edge, the corresponding line, LP2, P2 prime, will have to intersect LP3, LP3 prime. So actually what I'm going to get here, there will be 3 lines, one for each vertex, and if there is an edge here, they will intersect. So I need to look at configuration of 3 lines in R3, such that they are pairwise intersect. Okay, so what ways do I have to do it? So it can either be all concurrent or coplanar. There is no other way. Which means that the 2 triangles that I just drew must be congruent.
Okay, can you repeat that? So we have 3 lines that have to...
Yeah, I have 3 lines. One corresponds to LP1, P1 prime, LP2, P2 prime, and LP3, P3 prime. And if the graph has an edge, it means that, that this distance is the same as this distance, which means that the line that corresponds to P1, P1 prime must intersect the line. So you can forget about the points and say, okay, these are 3 lines, one corresponds to each vertex, and whenever there is an edge, it's 3 intersect.
Why can there be parallel?
So parallel is also intersecting, but we look at like generic configuration. But you're okay. So this somehow connects rigidity to. So you see that there is some connection, but still there are many problems. First of all, so I want to look now at the abstract problem. I want to forget about the points, just to take an abstract graph, to associate with each vertex of the graph a line in R3, and whenever there is an edge between vertex I and vertex J, to force the lines to intersect. And then ask maybe all these edges, all these constraints, force the lines to be concurrent, or force the line to be coplanar. Okay, and then I will know the original graph. So this is the general idea.
So can you always go the other direction? If you start with a coplanar construction or intersection, can you always construct graphs which are rigid?
So no, and this is one of the problems. So if you can start with, for example, with a set of n points in the plane, and then take all the pairs and choose 2 points, and you will get n squared lines in R3, but it's not clear how to go back there, because the way we interpret it here, n squared line is supposed to be corresponding to n squared vertices until we just. So no, it's not clear how to go back. And there are more problems. We don't always expect the lines to be concurrent, because we know that there is also rigidity. There are rigid graphs which are not globally rigid, and we still want to recognize them. So if we look at this configuration, so the distances are the same, but we cannot expect the lines to be concurrent or coplanar. So okay, so but what still can we say? Okay, so this one, let's try to state something more formally. Okay, so let's configuration. So a non-horizontal line in R3, I can identify a non-horizontal in C3, sorry. So if we have a line, we can parameterize it this way. way. So we can just identify such a line with a point in C4. So A, B, C, B, C. And now for a sequence of n lines, so for L1 to Ln, we can associate the graph GL
So we have now switched from R to C.
Yes. So we can associate the graph GL, what GL be, so the vertex set is going to be the number of lines, and so this is the set of the numbers 1 up to n, and the edges, so ij within E, if and only if Li and Lj intersect. Okay, so we can define such a graph. And then we look at the variety. So we define, so first look at this. So now given an abstract graph G, we can look at all the sequences. So we now write it like this: all the points in C are n, and I think of it as a sequence of n lines, such that so the graph that I started with is contained in the graph constructed this way. So L of x means the sequence of lines that correspond to this point x. So this is one requirement, and also that they are distinct, and the lines of Lx are distinct. Okay, and then x of g will be the Zariski closure of this. So we start with a graph, and we just take all the line configurations in C3 that realizes this graph. Realizes in the sense that every vertex corresponds to a line, and whenever there is an edge, the corresponding line has to intersect. Okay. And when we look at this variety, then we can find what we can say precisely what is the connection. Rigidity. So the theorem. So G is rigid if and only if this variety, so G is of dimension 2n plus 3. And it is globally rigid, so G is globally rigid. If and only if. So the irreducible components of xg that are of maximum dimension are contained in the set of, so we look at this variety x of g, and we look at the irreducible components of this variety which are of maximal dimension, and it must be contained in L of x or concurrent or coplanar. Okay. So these are the statements, but so far everything's okay. So these are the statements. So there is a very clear connection between the two notions, but this is not. I think this is not the important thing about this analogy between rigidity and configuration. I think that one thing that we can get from looking at the lines is simplify the proofs. So I want to show you. So as I said before with the observation, so one direction here is very obvious. So if this variety is of dimension at most 2n plus 3, then it's easy to show that it means that G is rigid. And also, if these are the only irreducible components of maximal dimension, then it's really pretty easy to show that generic configurations of the points must be congruent to one another, which means that G is globally rigid. But I want to use this direction in order to reprove the results that I mentioned.
So it could happen that the real part of this variety is smaller dimensional and
right. So in principle, it could happen that they will be of a larger dimension, and this still would be rigid because when you restrict it to R. So, but it doesn't.
But
it doesn't happen.
It doesn't happen.
It doesn't because it's an economics. Okay. So if the graph is rigid, then you know it doesn't happen for a reason.
So is it easy to characterize a variety?
Okay. To characterize the variety, what do you mean?
So you said if it's 2n plus 3 dimensional.
Right, so because it contains the configurations of the pairs of configurations of points as a subset, so it's easy to show that if it's not rigid, then you will find something which is of average. The other directions.